Hello, in this video we learn about geometry. So whatever you have learned in geometry in your high school and so on is applicable in this course. We learned that random variables, the space of random variables, the set of all random variables, they form a vector space, and also we'll have a geometry on them. So what is a vector space? If you have a set of entities where you can add them together, x plus y is meaningful and belongs to the same set. And also, if you could have a scalar multiplication, that means that this is a real number and you can multiply it by the entities of that set. So these two sentences together says that those entities, they form a vector space. Now, this is applicable to random variables because if you add two random variables, the result is a new random variable. And if you multiply a random variable by 2 or by a is a new random variable. So therefore, the set of all random variables is a vector space. So what is more important in this video is that we will put an equipment, a measurement tool on this space, which allows us to do geometrical calculations. Like if you could view a random variable as a vector, so this is your first random variable. This is for just our imagination. It will simplify. It doesn't mean that we could put it in a blackboard or something. And let's say this is another random variable y. So sometimes you want to calculate these angles, sometimes you want to calculate this length of this one, or project them, find the closest distance, or you want to put a circle, a parabola, all those things that you do in geometry, you want to do it on random variables. So we will introduce an inner product which allows us to do all the set topics. So inner product over a vector space is a geometrical instrument allowing you to calculate angles and distances between two vectors. So we refer to this instrument as inner product, which is a generalization of the dot product. So in any vector space, you could define the inner product of any two vectors. So the definition is that these functions, so this is one vector, this is another vector, and the inner product, the result of the inner product, this guy is a real number. So the inner product is a function from your vector space to the power of 2. So you have two inputs, x, y. So these guys are random vectors, and the output of this inner product is a real number. Okay? Or the dot product. This is a generalization of dot product. So it should have three important properties. The first one is linearity for x, which means that this equality should be satisfied for all vectors x, y, and z, and all scalars s. S is a real number. The second one is the conjugate symmetry. That means that if you change the order of these two guys, you should get the complex conjugate of this number. So because this inner product is it could be a complex number. In most of the cases in this course is a real number, but if it is complex, when you change the order, you should get the complex conjugate of that. Also, the inner product of any vector itself, it should be a real number and should be positive. So sometimes the inner product of a vector itself, we call it is length of the vector to the power of 2. We denote it by x to the power of 2 or Euclidean norm of that and so on. So these are the definition of a Hermitian inner product, or any vector space on which you have inner product. We call it Hilbert space or Hilbert product. So for random variables, we have a theorem. The set of all random variables denoted by R forms a vector space. We have proven that. The proof is easy. The second theorem is that this moment, which is the mean of xy, so remember that this is equal to integral of xy, the joint PDF of xy of x and y, and then dx dy, and double integral from y from minus infinity to plus infinity, and x also varies from minus infinity to plus infinity. So if we define the inner product, if the inner product is just equal to this moment, we will see that the space of random variables is has a dot product. So this gives lots of interesting mathematical properties. So remember that using this instrument, I could calculate the length of x. So if I want to calculate length of x, so this is, I calculate the inner product of x itself, a square root, I get length of x. Sometimes this guy, length to the power of 2, is called power of x. This is also power of x, because this is equal to the square root of the dot product of x and x. Now, if you want to calculate cosine of the angle between the two random variables, you could calculate that, because remember that the dot product of x and y is equal to the length of x, length of y, and cosine of, let's say, angle between them. Okay, so this guy is equal to this one, and this guy is equal to that. So you could calculate even the angle between the two random variables. So this is a geometrical interpretation of random variables, and believe me, whatever geometrical interpretation you use using this instrument, of course, properly, you get a good deep understanding into random variables. Now, using the same instrument, we could say, oh, two random variables are orthogonal. In your high school, you would use perpendicular. So you say two random variables, let's say x and y, are orthogonal if this angle is, the cosine of this angle is 0. So if cosine of theta is equal to 0, so this angle is pi over 2, that means that mean of xy divided by those lengths should be 0. So therefore, mean of xy should be 0. So we call two random variables orthogonal if the mean of their product is 0. So definition, two random variables are called orthogonal if the mean of their product is 0. So this is just a new definition. And we denote it. So this we say that, oh, they are orthogonal if they are, this is a notation, which is the same definition. And we call them orthogonal, uncorrelated. We call two random variables uncorrelated if their centered random variables are orthogonal. So if two random variables are uncorrelated and mean of their mean is 0, then we see that they are orthogonal. So orthogonality and uncorrelatedness is identical if they are having 0 means.